Hi, my name is Paul and welcome to Physics High. Today I'd like to go through the answers of the multiple choice section of the 2024 Physics HSC paper. Not only will I go through the answers, but also explain how we actually arrived at those answers. So let's get started. Our first question deals with circular motion, and we have a diagram where an object P is undergoing uniform circular motion, uniform meaning that the speed is constant throughout the whole rotation. Now we're asked which arrow shows the direction of the net force acting on P. In circular motion, the net force is always the centripetal force. Now that centripetal force is always perpendicular to the velocity at any one moment and is always acting in towards the center, so our answer can only be Y, which of course gives us C. Question 2. Which of the following provides evidence for the model of light proposed by Huygens? Now the model is a wave model, so we're looking for an experimental evidence that demonstrates the wave-like nature of light. The only other alternative is the discrete or the quantum or the photon model of light. Only one shows evidence of a wave-like model, and that is the diffraction of light. That as light passes through an opening, it bends around, which is a property of waves. So our answer is B. Which of the following is a fundamental particle of the standard model of matter? The standard model of matter says basically that fundamental particles are either quarks that make up hadrons, leptons, such as the electrons and neutrinos, and our bosons, which are force carriers, with the exception, of course, of the Higgs boson. So our response is looking for a particle that is indivisible, one of those particular ones. And so we can see a hadron, which is already stated, is made up of multiple quarks, so the answer is incorrect there. Neutron and a proton are both made up of quarks as well. The only possible answer left over is the photon, which of course is the electromagnetic force carrier. So our answer is C. The next question. We have a conducting coil that is mounted on an axle and placed in a uniform magnetic field, and the diagram shows different ways of being connected. And we're asked which of these setups actually allow the coil to rotate continuously. Now the first thing to notice is that all diagrams have a split ring commutator, and a split ring commutator of course reverses the current every 180 degrees, and this is important if you have a DC supply. And so automatically A and C are excluded as they're connected to an AC supply. B and D are DC, but we are having a coil that is in the position to show the maximum force. So if you're using your right hand palm rule, or you're familiar with the Fleming's rule, then the force in this section to get the force acting downward or upward is such where the magnetic field is perpendicular to the current. And so this is actually in its maximum position. So we want a current flowing. But according to the diagram, it's actually disconnected. And so B is incorrect, and therefore D is our remaining answer. Question 5. In this case, we're dealing with the HR diagram, and we have a situation where we are showing clusters X, Y, and Z of different ages. So these stars are all basically formed at the same time. So therefore, what are the ages of these clusters in order? So what we're looking for is evidence of older stars. Now, all three clusters have the main sequence. That is, these are stars undergoing hydrogen fusion to helium. So they're reasonably young, so to speak. But we also have evidence of the red giants, which are later stages of star development. And so therefore, any evidence of red giants or red supergiants, that will show it's older. But we also have evidence in one of them of white dwarfs, which is the end stage of red giants. And so therefore, using that information, cluster Y must definitely be the youngest. There's no evidence of old stars. Cluster X has evidence of red giants, so it must be second in its age, older. And then cluster Z, of course, has evidence of white dwarfs, and so that's the third one, which means our answer is A. Question 6, about the photoelectric effect. It says basically that the effect is mathematically modeled by this following relationship. That is, the maximum kinetic energy of the photoelectrons is equal to h of minus phi. Now, what is phi? And that's really what the question is asking. Well, phi is the work function. That is, it's the minimum energy required to liberate these photoelectrons from a metal. And if you look at our answers, the only answer, therefore, can be C. Question 7 is about half-life. And we're told we have a polonium sample, polonium-210, and it undergoes alpha emission to produce a stable isotope of lead-206. So in essence, what we are guessing is we have polonium-210, and that is converted to lead-206. Now the half-life is the time required for half of a particular radioisotope to decay into its other form. We have 138 days, but we're asked, what is it after 276 days? Well, after a one half-life, we have half of it decaying, so we would have a 50-50 ratio between the two. Because we have two half-lives, the polonium-210 now decays to a quarter of what it was originally. But that means the remaining 3/4 has to be lead-206, which gives us a ratio of 1:3, and the answer is B. Question 8 talks about an ideal transformer that produces an output of 6 volts when an input voltage of 240 is supplied. Now, what changes do we need to make if we want the output voltage to be 12, even though the input is still 240? Now, in essence, if we look at the input, which is 240, and that's the primary, and I'll call it the letter P, and then what we of course have is the output is 6, which of course is our secondary. Now, what that means is we have a ratio here of 40 is to 1 in terms of the turn ratio in order to get to 240 to 6. But we want actually not 6, we want to go from 240 down to 12 volts. And so what that means is I have either two options. Because the turn ratio determines the drop in voltage, both these cases are step-down transformers, what we want is a lower ratio. Now, I can do one of two things. I can either decrease the number of turns in my primary, or I can increase the number of turns in my secondary. Well, the only option I have available in those two options is B, and therefore a decrease of the number of turns in the primary coil will decrease the ratio and therefore increase the secondary voltage of the one we want, 12 volts. Question 9 is about projectile motion. And an object P is dropped from rest and an object Q is launched horizontally from the same height, and we're asked which option correctly compares the projectile motion of P and Q. Now, before we look at the answers, and I always advise my students, cover over your answers, try to analyze what's going on. We know that Uy of P and Uy of Q are exactly the same. It's 0. But Q, of course, also has a Ux, so it's moving horizontally. Because they are dropped from the same height, S, then that means the time it takes to go dropping is going to be the same, because remember, the vertical motion is independent of the horizontal motion. So both end up having exactly the same time to reach the ground. But of course, when it lands, the final velocity of y here is only going to be that vertical final velocity. The final velocity here is going to also be vertical down, but we also still have our initial velocity horizontally, which gives us, of course, a larger overall final velocity, which means our answer is B. Question 10. A rod is carrying a current placed in a uniform magnetic field and experiences a force. Now, how many degrees must the rod be rotated clockwise so that it experiences a force of F/2? Well, to solve that, we need to just write our formula for the situation, which is F is equal to BIL sine theta. Now, that means our original situation, because it's 90 degrees, what we have at F1 is equal to simply BIL, because the sine of 90 is 1. Now, we want half of this, which basically means I want my sine theta to be equal to 1/2. Now, that only can be if theta is equal to 30 degrees. So therefore, we wanted actually this rod to be in this sort of angle here, like 30 degrees. But that means my rod needs to be rotated 60 degrees. And so that's what we're asked for, and so the answer is C. Question 11. A satellite is in a circular orbit. What is the relationship between the orbital velocity and the orbital radius? The orbital velocity is equal to the square root of gm over r, where g is the gravitational constant, m is the mass of the planet, and finally r is the radius. We actually derive this by just deriving it by looking at the gravitational force and equating it with the centripetal force. What this means is if I take this gm out, this gm actually is a constant, I get that the velocity is equal to the square root of gm multiplied by 1 over the square root of r. Because this is constant, we have a direct relationship between V and the square root of the inverse of R, and therefore our answer can only be D. Question 12. A rod has a length L0, which is measured in its own frame of reference, and it asks which option represents the relationship between the speed of the rod V and the length of the rod as it's measured by a stationary observer. Now this is about length contraction. So in essence, the length is equal to L0, that is the proper length, multiplied by the square root of 1 minus V squared over C squared. That means this relationship clearly is not a linear relationship, so we can automatically exclude Y from our responses. As V gets greater and greater and greater, this number becomes closer and closer to 1, and therefore 1 minus this becomes a much smaller number than L0. So that excludes W. That leaves us X and Z. Now, if we look between X and Z, however, what this suggests is that initially, if the velocity is low, we will only have small changes. But because of the square relationship, the greater the velocity, the more marked that length contraction. And therefore, that excludes Z. And so therefore, our answer is B. Question 13. A diagram shows two identical satellites in A and B in orbit around a planet, and it says which row in the table correctly compares the potential energy U and the kinetic energy K of the satellites. Well, we know that there are two formulas that relate to those two types of energy. Now U is equal to negative G M over R. That means because this is negative, the further we go out, the greater the radius, the closer this gets to zero. So in other words, U is increasing as a result. And so therefore UB must be smaller than UA. But what about the kinetic energy? Well, the kinetic energy, of course, is equal to a half mv squared. But we know, just on a side here, that V equals the square root of Gm over R. And so we have another formula for kinetic energy, and that is G capital M lowercase m over 2R. Now in this case, the bigger the R, the smaller K gets as we move from B to A. And so therefore KB is actually bigger than KA. Now that only can be explained, as you can see, even though obviously I've swapped the letters around here, the only possible answer therefore is A. Question 14. The velocity of a proton is twice the velocity of an alpha particle, and the proton has a de Broglie wavelength of lambda. What is the de Broglie wavelength of the alpha particle? So what we're going to do is we're going to compare the two. And so what we say is the de Broglie wavelength of the hydrogen we want, and the de Broglie wavelength of the alpha particle, which I'm going to write HE here. Now in terms of the hydrogen or the proton, what we have is H over mv, where m is its mass and v, of course, its velocity. The helium nucleus, or the alpha particle, well, its de Broglie wavelength is H over, now the mass is 4 times greater, so we have 4m. But its velocity is only half of this one over here, so what we have is v over 2. And so in essence, what we end up getting is H2mv. So what does that mean? Well, this, of course, is the de Broglie wavelength of the helium. So the de Broglie wavelength of the helium ends up being 1/2 of the wavelength of hydrogen. And so therefore the answer is B. Question 15. A uniform magnetic field is directed into the page and a conductor PQ rotates about a end P at a constant rate. Now which graph shows the EMF induced between the ends of the conductor P and Q as it rotates 1 revolution from its position? You can use the right hand palm rule to work this out. Now if we put our fingers into the page or into the screen and use the thumb to represent the direction positive charges are moving, we're going to find that we're going to put our hand in the 3 o'clock position. Now of course electrons are the ones that are doing moving, but I'm using this as a conventional current idea. Now you'll see that your palm is now facing in towards P. That means there is an electromotive force causing positive charges to move towards P. Similarly speaking, of course, what really happens, of course, is the electrons therefore move from P to Q. But that means we have a potential difference. That means we have an EMF. And no matter what position that rod is in, that will always be the case. And so what we end up getting is a constant non-zero EMF, and the answer is D. Question number 16. The graph shows the relationship between the maximum kinetic energy of the emitted photoelectrons and the incident photo energy for 4 different metal surfaces. And we are told that the light frequency is 7 by 10 to the power of 14 Hertz and is incident on the metals. And we're asked from which metals are photoelectrons emitted. Now, to do this is determine the amount of energy in electron volts of that 7 by 10 to the power of 14. So what we say is that the energy is equal to, of course, HF, but of course, because we want this in electron volts, I have to divide this by 1.602 by 10 to the power of negative 19. That converts our answer originally in joules to electron volts. We now substitute everything in. And as a result, we end up getting 2.9 electron volts. Now that sits about here. Now reading from the graph, we can now read up and see that only K and lithium actually have a value for the kinetic energy for their photoelectrons. And so therefore the only possible answer is A. Let's have a look at question 17, and we have a cyclotron. Now, a cyclotron, of course, accelerates charged particles within these 2Ds. And the question asks for which of the following is true about the charged particle in the cyclotron. What we have is a magnetic field that causes these charged particles to rotate. That's what a magnetic field does to moving charged particles. But we have a gap between these 2Ds where we apply an electric field to cause them to speed up. Now we know that's occurring because the particle is not moving in a circular pattern that is in the same radius. That radius is increasing every single time as the velocity is increasing. So we have an electric field between the Ds that causes them to speed up, and a magnetic field, in this case, which is acting downwards because this is north and this is south over here, that is causing them to rotate around in a circle. That is, it's applying a centripetal force to the charged particles. Now, what that means is we're getting an acceleration between the Ds, but of course we're also getting an acceleration within the Ds because a centripetal force is being applied. So therefore there is a centripetal acceleration. And so, which is true, it increases in speed whilst in the Ds. Well, actually no, it's moving at a constant speed but traveling in a circle. So A is excluded. It says it only accelerates between the Ds. Well, I've just established that when the centripetal force is applied, there's a centripetal acceleration. So therefore, it's not only between the Ds. C, it undergoes acceleration inside and between the Ds. Well, that makes sense. So the answer ends up being C, but that's just check for D. It slows down inside the Ds and speeds up between the Ds. No, it doesn't slow down, turning at a constant speed, and so therefore D is excluded. Our answer is, of course, C. Question 18. And here we're dealing with the concept of both Faraday's law and Lenz's law. And we have a diagram here, and we want the same effect in X as it's done up here. So as the north enters this particular coil here, it's going to cause an EMF to be generated, and we're getting a current in the X coil. And as a result of Lenz's law, we're going to get an opposition. So we're going to have a north being generated on this side, and therefore a south on the other side. We want the same effect. Now, if you look at the diagrams, you've got to take close attention to the way that the coils are wired. All the X's are identical, so we're actually looking at the white ones. But you also need to be aware that we either have an increasing current or a decreasing current. So if it increases, then we're going to get the same effect. But if it decreases, it actually reverses the polarity of the magnet in terms of what you normally look at when you look at the coils. Let me explain. So what we have here is the coil is turning in such a way that if I grab it like this and I move the situation increasing in the current, you can see using my example over here, I'm going to get a south using this example, an increasing current. That'll produce a south here. Well, therefore A can't be correct because we want a north. What about B? Well, if I use my hand rule again, I'm going to use with a increasing current over here, and I again use my right hand grip rule, then what I'm going to have in this situation is I'm going to produce a north here, and I'm going to produce a south here. Well, that is exactly the same effect, and we don't want that. C. Now we've got this flipped over, but it says now decreasing. So if we use our right-hand group rule, you would probably point your north on this side and your south on this side. But this is decreasing. So that means I'm going to get a south here and a north over here. That means a north here, a south here, and we don't want that, and therefore it's incorrect. Let's confirm D. Similarly speaking, with a decreasing current, I'm going to initially thinking using my right-hand group rule a north here, but I'm actually going to get a south because it's decreasing in current. I'm going to get a south there and a north there. I'm going to get a south there, a north there, and that matches what we have up here. The answer is D. Question number 19. We have a vacuum chamber that has a uniform electric field and a uniform magnetic field. We have a proton entering that chamber that are actually moving with a constant velocity, and that velocity doesn't change, which means its direction doesn't change. So in essence, what's happening is that the force due to the electric field and the force due to the magnetic field are opposing each other, resulting in a net force. Now this reminds us, of course, of J.J. Thomson's work, where we have an electric field and we have a magnetic field, which is into the page. And then if I have a charged particle going into that field, you'll know that the electric field will cause a force on it downwards. The magnetic field, using the right-hand palm rule, will cause a force upward, and we have a net force that is a result of two forces in opposition of net force of 0. So we have FB here and FE right so. What happens though if I increase the velocity? And I'm going to use a blue pen just to highlight the difference. Now what happens, of course, is that the electric field will apply a force onto it that will give it exactly the same acceleration. Why? Because the electric field force is simply equal to EQ. The electric field is constant, the charge is constant. It's independent of velocity. But what about the magnetic field? Well, the force due to the magnetic field is equal to QVB. It's dependent not only on the charge, but also on the velocity. So therefore, what we end up getting is a much larger force due to the magnetic field. Therefore, we have a net force. So it's going to definitely accelerate in magnitude, because initially the acceleration was 0, and now the acceleration is not 0. However, as the force is greater due to the magnetic field than the electric field, what it's going to do is, because the fact that the force always going to be acting perpendicular, causing it to want to rotate. And so this charged particle doesn't stay in a straight line. It actually starts to curve, and therefore it will start to rotate. And that means, as a result, it's going to start actually changing direction, which means it has a centripetal acceleration, which means the acceleration is both changing in magnitude and in direction. So the answer becomes C. Our final question. We have 3 identical atomic clocks that are made so that they tick at precisely the same time, and one is kept in a laboratory on X. We have another one on Y, which is in a circular orbit with a period of 12 hours, and a third, Z, is in a geostationary orbit. These, of course, are all in the equatorial plane. Now, assume that the satellites are inertial frames of reference and the clocks are fixed only by the predictions of special relativity. Now, of course, this is not true. We also have general relativity acting on these particular clocks, but we're going to ignore that for the moment. We're simply applying our concepts of time dilation here. What we want is, what is the difference between X, Y, and Z? Now, the important thing is that if you observe it in your frame of reference, it's going to have exactly the same time. So first of all, for X, it's in your frame of reference, and so as a result, it's going to tick at your rate. What about Y? Well, it's moving with 12-hour period, which means it's actually moving away from you because you're having a period of 24 hours standing on the Earth. And so therefore, it's moving away, it's moving faster, it's going to be a slower time. So automatically, I can say the time for X is going to be greater than the time for Y. But what about Z? It's important to understand that Z is in a geostationary orbit. It actually is moving with you in the same time. In other words, this satellite is staying in the same position relative to you, meaning it's in your frame of reference. And as a result, the time is going to be equal to the time of X, exactly the same. And so therefore, the only possible answer is B. Well, I hope that's helped you understand the multiple choice section of this paper. My next video, I'll go through the short answer sections. Please remember to like, share, and subscribe, and put a comment down below if this has been helpful for you. My name is Paul from Physics High. Bye for now.